Hello everybody, we're going to look at the pair problem on page 120 straight from the textbook. So let's get a bit of you. And we are going to try using Foxit editor. So is this any good? So what do we got here? We're doing a second moment of area calculation for an I-beam. Oh no, don't do that. It's nice and symmetrical. So this one means that the neutral axis is going to be bang in the middle. I don't have to do any calculations here. So we've got a 60 long section here. Oh, okay, so everything's made out of 60s and 20s. So we've kind of done a Lego construction here. We've got 60 and 20, 60 and 20, and then 60 and 20. Nice and symmetrical. No requirement to do neutral axis calculations. And indeed they've done them for me here. So label this up as my first block. Yeah. This is my second one. And this is my third. Yeah, so you can see we've gotten 60, 20, 20, 60, 60, move it up a little bit, and then 20. So that's filled in all the dimensions. The areas are just going to be 60 times 20 multiplied each time, so these ones are all be the same. The y-centroids are interesting to see, so we got half of this, that will be 10. This one here, you've got to half your 60, so you're going to get 30, but then plus 20 on top of that, so that gives you 50. And then the top one will be half of 20, so that's 10, plus 60, so that makes 70, plus 20, that makes 90. Okay, so that's giving me my y's. Then I'm going to do a times y, I'm going to get these big numbers. And then to find the neutral axis, I'm going to add up all of these terms here. I'm going to add up all of these terms here. And then that gives me my neutral axis, as it says, as expected. It should be, I don't want you. And so it says, as expected, there 50 millimeters. So now we're going to go on to the next bit, which is to do the parallel access theorem components, and also the second moment of area components for the three rectangle sections. So we've seen previously that the b times d to the power 3 divided by 12 term will change depending on whether we're putting our beam this way or this way. So if my load is coming from above, I expect a bigger I if the beam is this way than if the beam is this way. And that's reflected in these results here, you can see. So we've got a breadth of 60 times a depth of 20 to the power 3, being multiplied there. And here we've got 20 times by 60 to the power 3, so that's giving me a much larger number. The one on the very top gives me the same value as the one on the bottom. So that's my b times d to the power 3 divided by 12 terms. Now my area times the h squared terms. Well, the one in the middle, the centroid rectangle section, is at the same location as the girder centroid location, so the h equals 0. Notice we drop any minus signs because we're taking this to be modulus. So the next thing is you want to look for is the distance away from this neutral axis here, which is at 50, back to the distances where the other centroids are. So this one was at what? So it's at a location. Have I got that right? Yeah, that's the location of 50 millimeters, and it's dropping down to 10 millimeters to get to this centroid. This one here is at the same location, and the one at the top will be the same. It will be 50, but this time it will be what? 90. So the h going back to the bottom will be 50 take away 10, so that will be 40 millimeters. And the h going to the top, I'll call that h3, will be 90 take away 50. Okay, you know, if you did 50 take away 90 and get minus 40, you just ignore the minus sign. So we get 40 there. It's not too bad as an editing tool. Right, so we've got some 40s here, an Adobe. And then we got a times h squared. So we've got some terms there, but we have no parallel axis theorem because we're not moving it from its natural, if you like, neutral axis. So I'm going to add up all these terms, my ah squared terms, add up all my b times d to the power 3 divided by 12 terms, add everything up, and then that gives me the second moment of area for the cross section. So add these up, add these up. Usually it's a good plan to add these up individually and compare them. I would be a tad worried, to be honest, if I got these results in the exam, because normally these are about the same order as these, but it's kind of a bit disguised because we've got 3.8 times 10 to the 6, and then we've got 440 times 10 to the 3, so we are 10 times out. So that's kind of like what you would expect typical values. So you'd expect these values and these values to be relatively similar on the whole for most problems. And we end up with this result. So notice this result is in terms of millimeters to the power 4. Notice I've always been working in millimeters all the way through. It just usually makes your numbers a bit cleaner and nicer to work with, in particular at this stage here. Yeah, not so much I suppose at this stage here because numbers become a bit crazy. But so for this stage you can see you get 60 times 20, so you're going to get reasonably sensible integer numbers. You can work with a sensible integer for your y value, and you can work with a sensible integer for your h value as well. So that's the advantage of working in millimeters. So your final result, if you needed to convert it back into meters to the power 4, usually what happens is that this result becomes times 10 to the 6 or 10 to the 9. You usually get those sort of kind of values, and you just need to knock off 12. So if it becomes out as 10 to the 6, you just flip it, make it times 10 to the minus 6. 6 take away 12 is minus 6. And if this result comes out as, say, times 10 to the 9, so normally they're those kind of values, then 9 take away 12 gives me 10 to the minus 3. So that's an option you can just do then, and then you've got your result in meters to the power 4. So your value from your bending moment diagram, typically you probably want to deal with that in terms of Newton meters. So that's the point that I would then convert it into meters to the power 4.